Have you ever really thought about this? Right now, you might feel like you're sitting perfectly still, but you're also hurtling through space at thousands of meters per second. How can both be true? Well, we're about to find out as we break down the physics of motion. Let's get into it.
Here's our game plan. We'll start with the huge idea that all motion is relative. Then we'll get into the nitty-gritty, talking about distance versus displacement, speed versus velocity, and finally, what happens when things start speeding up or slowing down.
All right, let's kick things off with a simple question that has a surprisingly deep answer.
So, seriously, are you moving? You're probably thinking, of course not, I'm sitting here watching this. But in the world of physics, the answer isn't a simple yes or no. It really all depends on your point of view, what we call your frame of reference.
Think about it like this. Imagine you're standing on the sidewalk and a bus drives by. To you, the people on that bus are clearly in motion. But what if you were on the bus? The person sitting right next to you, they're not moving at all, are they? They're at rest relative to you and the bus. And we can scale this idea way up. We feel totally stationary, but that's just because we're moving right along with the Earth. If you could somehow watch us from the sun, you'd see our entire planet and all of us on it rocketing through space at a staggering 30,000 meters every second. So here's the absolute key. Motion is always described in relation to something else. An object can be moving and at rest at the exact same time. It just depends on who's doing the looking. There's really no such thing as absolute universal stillness.
Okay, so with that idea locked in, let's build on it. It's time to get a little more precise about how we describe a journey.
First up is distance. This one's pretty straightforward. It's the total ground you cover. Every single step, every twist and turn. It's what your fitness tracker is counting.
Displacement, on the other hand, is kind of like the physicist's shortcut. It doesn't care about the scenic route you took. All it cares about is the straight line from where you started to where you ended, point A to point B. That's it.
So picture this. You take a long, winding path through a park to get to your friend's house. You walked 20 meters. That's your distance. But if your friend's house is only 10 meters away as the crow flies, your displacement is just 10 meters. This actually leads to a really interesting little brain teaser. Is it possible to travel a really long way but end up with zero displacement?
You bet it is. Think about a runner on a 400-meter track. They run a whole lap. That's a lot of distance. But where do they finish? Right back at the starting line. Their start point and end point are the same, so their displacement is a big fat zero. So let's just nail this down. Distance is the total path you took. It's just a number. We call that a scalar. Displacement is the straight line change in position. It's a number and a direction. That's a vector. And yep, displacement can be zero even if you ran a marathon.
Okay, perfect. Now that we've got distance and displacement sorted out, we can tackle two other words that we often use interchangeably but mean totally different things in physics: speed and velocity. Speed is exactly what you think it is. It's how fast you're going. It's just the distance you traveled divided by the time it took you. And because it's based on distance, speed is just a number, a scalar, no direction needed. Velocity, however, is like speed's much more precise older cousin. It's calculated using displacement. And since displacement has both a value times and a direction, so does velocity. It tells you how fast you're going and which way you're headed. And this brings us right back to our runner on the track. During that 400-meter lap, their average speed was obviously pretty high. But because their total displacement was zero, their average velocity for the whole lap is also zero. Weird, right? But, motion is rarely that simple and steady. We speed up, we slow down, we turn corners, and that's where our next big concept, acceleration, comes into the picture. Now, this is so important. Acceleration is any change in velocity. This is key. So, yes, speeding up is acceleration. Slowing down is also acceleration. And here's the one that trips people up. Turning a corner, even if you keep your speed exactly the same, is still acceleration. Why? Because you changed your direction, and if you change direction, you change your velocity. Think about being in a car. When you hit the gas, you speed up and feel pushed back in your seat. That's positive acceleration. When you slam on the brakes, you slow down. That's negative acceleration, which we often just call deceleration.
All right, we're on the home stretch. Let's put all these ideas together to describe the two main types of motion you'll see in the world.
First, you have uniform motion. It's smooth, it's predictable. Think of a car on a perfectly straight highway with the cruise control locked in. It has a constant velocity, which means its acceleration is 0. Then you have non-uniform motion, which is, the rest of real life. Driving in a city, you're speeding up, slowing down, turning. Your velocity is always changing, which means you are constantly accelerating.
And that's really the heart of it all. Everything we've talked about starts with that one idea, your frame of reference. From there, each new concept just adds another layer of detail, telling the complete story of how something moves.
Which brings us back one last time to our runner on the track. Why do we even need both distance and displacement? It's because they tell us different but equally vital parts of the story. Distance tells us about the effort, the energy burned, the total journey taken. But displacement, that tells us the net result, the ultimate change in position. In physics, both the journey and the destination matter.